Now we'll take a look at an example where they actually provide the data they collected. So it says a researcher selects a random sample of 10 Chester's churros. The number of calories in each churro follows. Assume the variable is normally distributed, and this statement is required normally distributed because our sample size is small. So in general, when our sample size is below 30, the original distribution needs to be normally distributed in order for our central limit theorem to apply. All right, so that's the first step here. The original population is normally distributed. And then the standard deviation of the population is given to be 30. So this statement, assume the variable is normally distributed with a standard deviation. What they're saying here without using the word is that there's this assumption that we know the population standard deviation. So this standard deviation is not for these 10 churros, it's a general statement that we are to assume this is the true standard deviation of our population. So that's important because if this was not the population standard deviation, we'll need to take another approach. So it becomes more clear the more problems we do, what we're looking for. So let's keep going. We're going to be looking for a 95% confidence interval estimate for the true mean number of calories in his churros. So we know what's true for the 10 churros, and we're trying to draw a conclusion about all churros that he makes. All right, so we'll start with the parameter. So we would like to know the unknown population mean. So the mean of all of his churros, and that would be represented by mu. Population mean is our parameter. And then we know that our best point estimate, so our best single number that estimates that mean, is its corresponding sample statistic. And so in this case, the sample mean. All right, so based on this data, let's find the best point estimate for the mean. So we would enter the data into our calculator. So I have done that already. So if you want to pause and get that data into your first list, I'm going to find that mean by using one bar stats, just to review that process. So I'm going to go stat, calculate, one bar stats. And if your data is in L1, we can just hit enter. And then I see that for this sample, the average came out to be 321 calories. So 321 calories is my point estimate for the mean of all churros made by Chester. All right, so that is the value that is the center of our confidence interval. So X bar, point estimate in the center. And then the population standard deviation, again, is known. We are to assume that even though we don't know the population mean, they want us to assume that the population standard deviation is 30. So we're getting to problems shortly where we won't know sigma, which is more typical because if you don't know mu, you generally wouldn't know sigma either. But this scenario, it is given. All right, and we're ready to make our confidence interval. So if you have the data, when we run our Z interval, and the Z interval applies because we do know the value of sigma, when we enter the input, so I'm going to bring it up on the screen here. So stat, tests, number 7, Z interval. You're going to switch your calculator over to input data. So the input into the calculator, we've got all of our data. We've entered that into L1. So we need to enter sigma. So we'll put our 30 in for sigma. And then where you put your data, and we usually just go ahead and put it in L1 as I did. For frequency, that's always going to stay 1. It means there's 1 of each number. And then the confidence interval, we're using a 95% confidence level, so 0.95. And then we are ready to calculate. All right, you'll see it gives us X bar. It also gives us S, the sample standard deviation. So we're going to be returning to that in a bit. Gave us our sample size of 10, and then of course the interval itself, and we're going to round to 1 decimal place up here, round to 1 decimal place. So 302.4. So we believe that the mean for all churros made by Chester, we think that the true mean is somewhere between 302.4 and then 339.6. All right, so our lower limit is 302.4, our upper limit 339.6. So always good to point out regarding symbols that this was X bar. This is what we know to be true for sure. We know the mean was 321 because we have data. But the symbol here is mu. That is what we're estimating because we haven't collected data from every churro made by Chester. All right, so let's do a little sentence summary here. So based on a sample of 10 churros, we estimate with 95% confidence that the true mean number of calories and I'm going to add some in all again. So it's always good to remember this is what we think is true for all of them. So the mean number of calories in all of his churros is between 302.4, lower limit, and 339.6. All right. Now, the 95% confidence means that if I were to take a sample of 10 churros like we did here, and we do it over and over and over again. So we pick 10 churros, and then we pick another 10 churros, and then a different 10 churros. If we kept looking at samples of 10 churros and we created confidence intervals, 95% of the time, this value for mu will be within that interval. So we don't know for sure that the mean is between these two numbers. We just know that 95% of the time that we do this process, we will get an interval that contains that mean. So it says Chester claims his churros average 300 calories. Does our confidence interval contain this value? So 300 is not between these two numbers, right? 300 is below 302.4. So I'm getting the impression that Chester could be wrong. He says that the average is 300, but I'm 95% confident the average is actually higher, somewhere between these two values. So that is the general idea with inferential statistics. When we use a sample to approximate a population parameter, we're not 100% sure we're correct. And in this case, I would challenge Chester and say, I know you say the average is 300, but based on my research with these 10 churros, based on my research, I think that the mean is actually higher and somewhere between those two values. Okay, so let's say that you would like to do your own study on his churros rather than relying on this data. So our next step is to say, if you wanted to do your own study, how do people decide how many churros to include in their sample? So we just did an example with 10 churros, and now we're going to talk about a method for figuring out the sample size you'll need in order to reach a desired level of confidence and as well a desired margin of error. So before I do that, I would just want to come up and find the margin of error in this last example. So we know the lower and the upper limit, and we know the margin of error is the distance from that sample mean to the lower and upper limit. So there's different ways you could find E. You could just find the difference between those two values. And I would say generally that would be the quickest way. So for me, I would just say 339.6 minus 321. So let's see what that distance is. So 339.6 minus 321. So it looks like the margin of error is 18.6 calories. So this distance, 18.6, this one would also be 18.6. And now when we do our study, what we're going to do is say, you know what, this margin of error is too big for me. I don't want an estimate that has quite so large a margin of error. And let's see what happens in that case. All right, so we want to conduct our own study and determine how many churros we need. We'd still like to be 95% confident in our estimate of the true mean, but we also want our estimate to be within 8 calories of the true population mean. And we want to find the minimum necessary sample size. Okay, so let me just start with writing down the given information here. So we're going to do a 95% confidence interval. I'm going to write down that critical value, Z alpha over 2. That would be 1.96. And when they say accurate to within, within is your plus or minus. So that's your margin of error. So we'll do E for margin of error. And when it says find the minimum sample size, that means we're looking for the lowercase n, number of churros. All right, so we didn't do this one by hand for finding the margin of error, but we could have. I'm just going to repeat that formula that we did before. You could find the margin of error by using the Z alpha over 2 times sigma over the square root of n. So what we're going to do is, for this formula, we want to solve it for n, because now we're looking for n and we're going to be given the other information. So the only other thing I want to point out, there is a sigma here that's going to come up. And so we are staying with this example where we're assuming that the population standard deviation is 30. So I'm also just going to make a note here that we're assuming their sigma is 30. All right, so I'm going to solve this equation for n and save you a little bit of the algebra. So when you solve for n, what we'll get in parentheses is the z-score times sigma. That will be divided by the margin of error, and that whole quantity is squared. So eventually here, when you're solving to get rid of the square root over the n, you end up squaring both sides. So that, you can do the algebra if you'd like, but that is our formula for finding n. All right, so I'm going to just enter this on the paper like I do on the calculator. So Z alpha over 2, 1.96 times the sigma value, 30. And then I divide by the desired margin of error, which is 8. And I close parentheses and square. All right. So let's check that out. 1.96 times 30 divided by 8. Typo there. Typo there. All right, 1.96 times 30 divided by 8, close parentheses, square. All right, and we're getting 54.0225. So a couple comments about that number. So n is the number of churros we need in our sample. And it says the minimum necessary sample size. So here is the deal. This is how many churros we need. So if you are selecting churros, this has to be a whole number, like 10 churros or 12 churros, whatever that number is. It has to be a whole number that you're picking. So the rule is, in order to keep our accuracy and in order to keep our confidence, we can't use normal rounding when we look for our whole number. So basically in statistics, the more data you have, the better off you are. So even though 54.0225, normally rounding this whole number, you would get 54, but that's not what we do here. So anytime there's any decimal portion, we need to always go up to the next whole number. So we always go up the number line. So 54, I don't care what that decimal part is, we go up to the next whole number. So you would actually need 55 churros in your sample in order to maintain your confidence and your desired margin of error. All right, so this always seems weird to students because you're thinking rounding, and it's not really rounding in the normal sense. You could call it, I like saying go up to the next whole number. You could also say round up always, no matter what. So no normal rounding rules when you're looking for your sample size. So remember, more data is better. So this is at minimum, you're going to need 55 churros. It'd be better to take a sample of 500 churros. So basically, you're usually limited by your budget and practical restrictions, but we're looking for bare minimum sample size. We would need to go up to 55 churros. So the margin of error in the last problem, their margin of error, 18.6 calories, and we changed to a smaller margin of error. So if we want to improve our accuracy, you're going to need more data. And that's why the answer before was 10. And our answer is bigger than that because we would like to be more accurate when we are done with our study. All right. And so that is how we find the sample size needed.